Hi. So today we are going to be officially starting our unit on probability. We did do a little preview video of that last week, but I just wanted to make sure that you knew that this is now new stuff. This unit is all about probability, and so you might have some awareness of the idea of probability from people just speaking in normal day-to-day life. Probability values can range from 0 to 1, or as percents from 0% to 100%. And so I have a picture here that kind of shows you the scheme of that. And our last two units in this class will focus a lot on probability, not entirely, but there will be an element of probability in all of it. So I have some notes here for you, and you can take notes on your own paper, or on Schoology there is a document that you can use. If you happen to have a printer at your house, you could print that out and then take notes on that. It's a like a formatted page for taking notes, but you don't necessarily have to have that. I know I don't have a printer at my house, so don't let that get in your way. You can just listen and take notes as you wish. Okay, so probability and randomness are really important to both setting up and understanding statistical results. So as we talked about in Unit 3, we need our sample to be selected with randomness. So randomness is a key idea for when we are picking our sample for sure. And then once we have our sample, we're going to get some data, and we're going to have to decide if that data is important or not, if it's something that we would expect or not. And so what we need to determine then is if our results are what we call statistically significant. And so a statistically significant result is one that is different enough from what we would expect just through random variation. So an example that I use a lot, and I think this is because I have seasonal allergies and it's spring right now, and so I think that's why it comes to mind for me. But if we were testing an allergy medication, and let's say that I was part of that trial, and several weeks, into taking this medication, I'm like, my allergies seem better. Now, how much better? Is it better just because I'm indoors a lot? Is it better because the pollen count happens to be low? Is it different enough from what we would expect with random variation? That is our question. And that is called a statistic. If the answer to that is yes, then our result is said to be statistically significant. But that really comes down to what we can expect through probability, right? What would be the odds that I would just have a better allergy season anyway? Okay, so we're comparing that to what we would naturally understand to happen. Okay, a random phenomena. This is, again, a lot of vocabulary, kind of like at the start of any unit. We have to kind of pin down our vocabulary. So the term a random phenomena is given to any situation where we know what the outcomes could possibly be, but we don't know which outcome is going to happen. So an example of this would be driving up to a traffic light, or as my husband from Wisconsin calls it, a stop and go light. So a traffic light, we certainly know the options of what is going to happen when we pull up to the traffic light. We are either going to see a red light, a yellow light, or a green light. And so the thing is, we're not really sure which light we're going to see, right? If I'm sitting here in my house and I'm thinking, I'm going to drive up to the Jewel later and go grocery shopping, I don't know when I get to the intersection which color light I'm going to see, but I'm going to see one of them. That makes it a random phenomena. So another example of a random phenomena would be rolling a die. Another one would be flipping a coin. So anything where I am very sure of the full set of options, but I don't know which one is happening, is going to be called a random phenomena. Okay. Oh, I didn't remember that I already had written this. Okay, we're going to go little by little here. Okay, so there are some vocabulary words that I'd like to go through, and then we're going to go through these same vocabulary words, but thinking about rolling dice. Okay, so vocabulary. A trial is any procedure that can be repeated and that has well-defined outcomes. So a trial might be something like flipping a coin, right? Every time I flip a coin, that coin flip is something that I can repeat, and it has well-defined outcomes, either heads or tails. An outcome is a possible result of that trial. So if I'm flipping a coin, the outcomes would be either heads or tails, right? So every trial, every time I repeat a certain action, I'm going to get a certain outcome from that trial. An event is a set of outcomes that could come from, oh, I wrote event there. I really meant trial. Otherwise, I'm going in a circle there. Sometimes you find the mistakes, you know, when you read it over yourself. I'm sure you've had this experience in writing papers and such. Okay, so a set of outcomes that could come from a trial would be the event. And sample space. This is a very key idea. Okay, this is going to come up all the time. So sample space is a list of all the possible outcomes, okay, for any given scenario. So now let's go through those same vocab words again, but let's think about the idea of rolling 2 dice. Okay, so this was mentioned in the video that we watched recently. Okay, so if I'm rolling 2 dice, the dice I'm thinking of, by the way, are like your standard dice that are shaped like cubes, right? So each side, the sides are 1 through 6, right? Okay, so each die has the numbers 1 through 6. Okay, so a trial in this scenario would be rolling the dice. An outcome is going to be any pairing of numbers that could happen. Okay, so I'll write that. Okay, so an outcome might be rolling a 2 and a 5, for example. Okay. An event might be, let's say I want to find the probability of rolling a 7. So the event would be rolling a 7. And so the distinction here between outcome and event is outcome could have a lot of different options, like getting the 2 and the 5 is part of the event of rolling a 7. So the outcome 2 and 5 is within the event rolling a total of 7. Okay, but there are other outcomes that would fit inside the event, such as rolling a 1 and a 6, a 6 and a 1, a 3 and a 4 and a 3, right? So there are many outcomes that would fit inside the parameter of rolling a total of 7. Okay, the way that we typically would write the probability question that I just mentioned is you write a capital P and then you can write a description. Or sometimes you might see probability of getting 7, right? Something like that. But the capital P in this context indicates that we're talking about probability. All right, and then the sample space is the listing of all the possible outcomes. And if you think about the fact that we have 2 6-sided dice, each die has 6 different faces to it. And so there are going to be 36 or 6 times 6 ways of those dice showing up. Okay, so it's the listing of all, in this case, 36 outcomes. And notice I said outcome there, not event, right? There's not that many different ways. There are not 36 different totals that could happen, right? There's like 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the different outcomes that could happen. I actually said that wrong. Those are the different events that could happen, right? The event of rolling a 2, the event of rolling a 3, the event of rolling a 4, total, right? Those are the different possibilities. I could get a 2 through a 12. And then there's 36 different outcomes, right? Different pairings. All right, let's move on. All right, the law of large numbers, okay? So there are 2 kinds of probability, basically. There is experimental probability and theoretical probability. So experimental probability is when you actually do an experiment. So let's just have like a little side note here. Let's put that over here. Okay, so experimental probability is when you actually collect data from an experiment. So something that you do, right? So like in rolling dice, I might say, okay, sit down and roll these dice 100 times, keep track of what happens on each roll, and then figure out what fraction of those were a total of 7. Okay, that's doing experimental probability. There is also something called theoretical probability. And that's where we're using math. Okay? And we're saying, all right, there's 36 different ways to roll the die. How many of those different trials or how many different outcomes are going to yield a total of 7? And then based on that, we say, well, this is what we think the incidence of rolling a 7 would be. Okay, so that's the distinction. It's either like collecting your own data or using sort of the theory, it's right there in the name, the theory of how many different outcomes should be a given thing. So the law of large numbers just says the more trials that are performed, the closer these values will get to each other. Okay, so the thing is, sometimes people will try to misapply this idea, and the misapplication of this idea is what we call the gambler's fallacy. The gambler's fallacy is thinking that the law of large numbers applies in the short run, so that the percent of heads versus tails in coin flipping has to always be going closer and closer to 50%, even if you only flip the coin like 6 times. That's not necessarily true. Streaks can happen in the short run. And it doesn't mean that the coin is weird or that, you know, there's some kind of voodoo magic happening. That it doesn't mean that at all, okay? So the gambler's fallacy is the error in thinking that the law of large numbers applies in the short run. Right, so the example I just made up off the cuff was flipping a coin. So you flip a coin, say 6 times, and say this is the outcome, right? I got heads, 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 tails, heads. People might be like, ooh, the coin's hot, right? I'm getting a lot of heads, put money on heads, right? If that were like a casino game that you were betting on. And that doesn't make any sense, right? This is only 6 coin flips. In the long run, go back to the law of large numbers. In the long run, we know that the coin flips are going to be about 50-50 if you do enough trials. So just doing 6 trials, that's not telling me anything. That doesn't mean the coin is like strange in some way. The coin is a 50-50 coin where it's 50% heads, 50% tails in the long run, not necessarily in the short run. All right, so the actual definition of probability, I thought I should probably include that, is the measure of the extent to which an event is likely to occur, and it's found by taking a ratio. That ratio is going to be the number of, I guess I would call it winners, over the total number of possibilities. And that total number of possibilities, that is the size of your sample space. So that's the formal definition. Sample space is the set of all possible outcomes for an experiment. So if we were looking at a deck of cards, 52 would be the bottom number in my fraction, because that's how many cards are in a deck of cards. Now, a lot of problems do use the idea of a deck of cards, and so you really should have some awareness of the deck of cards, and this is a great time to, learn to play some card games if you don't have that experience. There are 3 cards in each suit that are called face cards. Those are the Jack and the Queen and the King. Those are called face cards because they have faces on them. The Ace is not a face card. The Ace in some games is a high card, in some games it's a low card, and sometimes you get to pick. There are 4 different suits. There are 2 suits that are black suits. They are called spades and clubs. And there are 2 suits that are red. They are called hearts and diamonds. Now, you should just have some awareness of what is in a deck of cards, okay? Just because it's an easy kind of question to come up with in terms of just checking your understanding. We actually talked about both of these on an earlier slide. I got a little ahead of myself, right? So experimental probabilities, when you do an experiment, theoretical probability is based on what we expect in the math. So this one is asking us to find theoretical probabilities. So no, you don't have to go find a die or go find a coin. That would be if we were doing experimental. I'd ask you to actually do some tosses and rolls, okay? But this is based on theoretically. So for example, flipping heads on a coin, I know that there are 2 outcomes in my sample space, heads or tails, and one of them is heads. Rolling a 6 on a standard die, I know that there are 6 sides to the die, right, because it's shaped like a cube. The cube has 6 faces, and one of those sides has 6 dots, so that's 1 out of 6. Rolling an even number on a standard die, well, the numbers on a standard die are these, and the numbers that are evens are the ones I just circled, so that's 3 out of 6. Now, everyone always asks me, do I have to write like this as a fraction, as a percent, as a reduced fraction? I don't care. You can write this as a half. You can write this as 50%. You can write this as 0.5. Those all express the same number. I don't mind. You can write it in any form that you wish. Now, do watch, because we might have like the Quizlet for Unit 4. That would be the one exception, right? Because of taking assessments online, there might be a time when my directions say, write this as a decimal, write this as a fraction, right? Because of the interface, right? So just make sure that if it does say something, do express it that way. But generally speaking, I don't care which way you write it. It's all the same idea. Okay, there are some questions that are coming up that I'd like you to kind of pause and then check. Okay, so I'm just going to trust that you can do that. So right now, take a second to pause the video and try these problems. Okay, so hopefully you tried those on your own. I left these as non-reduced fractions. You certainly can reduce every one of them. So this reduces to a fourth, this reduces to a half, this reduces to 1/13, right? If you did reduce it, or you could write it as a decimal, that's okay too. Okay, here are a few more questions. Again, I'd like you to pause, try, and then come back and see if you got them right. Okay, here are my answers. So there are 2 red 2s in the deck. So I said 2 out of 52. You can reduce that if you want. An even numbered card, we want to think of the fact that there's 2, 4, 6, 8, 10. So that's 5 out of every 13 cards. There's 13 cards in a suit. Or you could say there's 20, right? Because there's 2, 4, 6, there's 5 in each suit, and there's 4 suits. So that's 20 out of the deck of 52. And then the last one on this slide, drawing a number less than 4. You can see my thinking in the green pen there. 2 and 3 are less than 4. I didn't include 4 because it said less than 4. It didn't say less than or equal to 4. I didn't include the ace because the ace is technically not a number. Okay, ace can be high or low, so I took the ones that were numerical. Okay, this one is about some marble, has some marble questions on it. Again, I'd like you to pause and then come back. Okay, so hopefully you got these right. Probability of green, 2 out of the 8 marbles are green, green or red. So notice that with the or, what I ended up doing is taking the green and the red and then adding them together. So or in probability is going to actually indicate adding. That's super weird. I know that. Usually and indicates adding. That is not the case in probability life. And then red or yellow, combine those by adding, and you get 6 out of 8. Let's do the rest of these marble problems. So the next one says the probability of drawing blue. Well, there aren't any blue. So I'd say there are 0 blue out of 8, or just 0. This answer is the answer that means impossible. Probability 0 means it can't happen. Impossible. The next question says, what is the probability of drawing red or green or yellow? Well, I just told you that or is when you add. So if I add the red and the yellow and the green, I get 8 marbles out of 8, which is 1, which as a percent is 100%. And that means certain. There are not a lot of things in the world that are absolutely certain, but it is certain that if you were to draw 1 marble from that jar, you would get a marble that is red or green or yellow. So in probability problems, hopefully this reminded you that the largest possible answer is 1. 1 as a percent is 100%. And the smallest possible answer is 0, and 0 as a percent is 0%, as we just saw from those examples. All right, so in the last question, if you look back for one quick sec with me, there were 2 greens. So the probability of drawing a green marble was 2 out of 8. And the probability of getting red or yellow, if you look back here, was 6 out of 8. And if you look at those 2 together, 2 out of 8 and 6 out of 8 together, cover all of the possibilities, 100%. So either my marble was green or my marble would be not green. Green and not green are what we would call complementary probabilities. Together they add up to 100%. They cover all of the outcomes in the sample space because my answers, my colors, I should say, were either red or yellow or green. And so if I say green and I say not green, that covers everything. There isn't some other secret 4th option, right? Green and not green are it. So that's called complements. Complements are very useful in problems because there are times when answering a question, like it's easier to answer the opposite. For instance, my classic example of this is my husband does like to cook. And so sometimes he'll turn to me and say, what would you like for dinner tonight? And it's so much easier for me to tell him what I would not like for dinner because there are many things I would enjoy for dinner. And so to go through that list would be, an exhausting proposition. So maybe I just say, you know what, let's not have red meat, right? And then he knows that everything else is possible, right? So sometimes we answer the opposite problem in order to actually answer a question. And that's the idea of a complement. So with complementary probability, if I want to find the probability of something, sometimes I say, okay, take 100% or 1 as a decimal and subtract the other, like the opposite probability, the complement, okay? Bear that in mind, that's going to come up. You do have a problem set to try, and thank you for listening.